Okay. Assalamualaikum. Good afternoon. Okay, for today class, we may refer to Dr. Kamaruddin reference book. Okay. So I guess I have discussed or explained, okay, by using the slide presentation for our last class. Okay. So now we look on Dr. Kamaruddin reference book. Okay. On the chapter 3 on slope stability. Okay. So this is the not the recent version. Okay, perhaps there will be an additional what we call as example. Okay, on Dr. Kamaruddin, the new one. Okay, so let's say if the content is not similar with uh, the one that you have. Okay, so I hope one of you could scan and share it to me. Okay. Okay. So, okay, on the theoretical background, a slope is defined as a soil surface that makes an angle with respect to the horizontal plane. Okay, slope can be natural, such as hill, or man-made, such as embankment. Okay. The main concern with regard to the slope is the stability against failure. To facilitate stability analysis, slopes are categorized into two. Okay, where we have here infinite and finite slopes. Okay. So the discussions or explanations I have discussed previously. Okay. So at least when you read this paragraph, so you already have the idea. Okay. What is the definition of slope? Okay. What is the main concern? Okay. And what type of slopes? Okay. So we go for the infinite slope. Okay. An infinite slope possesses a constant inclinations, okay, of the an ultimate unlimited extent and uniform condition, okay, at any depth below the surface. The failure plane forms when there are significant changes in soil properties between the moving and the stationary soil masses. Consider an infinitesimal having a width B and average height H. Keep in the mind that the stability analysis of infinite slope involve interpretations of the developed shear strength and shear stress along the failure plane. The basic equation to be used in the stability analysis are as follows. Okay, so this is the list of the formula. Okay, are used to determine the stability for the infinite slope. Okay, so we have here normal stress. Okay, then we have here shear stress, and then we also have here shear strength. Okay, so the ratio between the shear strength and also the shear stress is the factor of safety. Okay, the above equation are derived based on the slope diagram in figure 3.1 and may be manipulated to suit the given condition, okay, which are granular or cohesive soil with and without seepage. Okay, so seepage means that there is a groundwater level, okay, or the water movement. So in the slope for the infinite, okay, so we may assume that the seepage is parallel to the slope surface. Okay? Although in reality, it doesn't show that kind of conditions. Okay? So then we have here sigma, the normal stress, tau, the shear strength, the shear stress, and then later on from the normal stress, we can calculate for the what we call as for the shear strength. Okay. So in order to get the value for the shear strength, so we need to use the parameter of C, phi, and also gamma. Okay. So I is the what we call is the inclination or the gradient of the slope. So equation 3.1 to 3.4, okay, is the conditions for the cohesive soil without seepage. Okay? So means that there is no groundwater, okay, at the same thickness, okay, inside the thickness of the uh, slope structure. Okay? So what happen if there is a seepage? Okay, so we may use the equation 3.5 to 3.8. Okay. For the first one is the effective normal stress. Okay. So we need to use the value of effective, okay, to get the normal stress value, the effective unit weight to get the normal stress value. Okay. So that's why we need to assume that the CP is parallel to the slope surface. Okay. Then we have a tau, which is the shear strength. Okay. And because the shear stress, because the water uh, doesn't shear, okay, so that's why we not exclude the water, okay, under the shear stress. Okay. Then we have a shear strength, okay. So in this case, we may use the effective value, okay, due to the water could be compressed, not shear. Okay. So that's why we need to eliminate the 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 unit weight of water. Okay. So 3.5 to 3.8. Okay. Okay, then for 3.2.3, granular soil with seepage parallel to the slope surface. Okay, so this is a granular condition. Okay, and there is water, okay, or seepage which is parallel to the slope surface. Okay, so starting from 3.5 to 3.8. Okay, so the difference is on the 3.9. Okay, because under the granular soil, it doesn't contain of cohesions, okay, because it is a cohesiveness material, okay, like sand or gravel, okay. So 3.9 doesn't contain of C. Okay, granular soil without seepage, okay, similar to 3.9, okay, where it doesn't have a C, okay, but the value for the seepage, okay, is not considered as well, okay, in the 3.2.4. Okay, so that is for the infinite slope. Okay. Although you can easily, okay, use a simplified method, okay. However, okay, you need to understand what is the limitation of the simplified equations. Okay, some of the equation, okay, is not, I mean, to cater for the seepage below the slope surface. Okay, so that's why it is better for us to use the raw formula. Okay, then creep until it have the ratio between S and tau. Okay. Okay. So that's for the infinite slope. Okay, then we have a finite slope. For the finite slope, the inclined surface of finite slope is limited to an unspecific height. Unlike infinite slope, the failure surface of finite slope are generally in the form of circular arch. Okay, so this is the common uh, methods, okay, used to determine the factor safety for the finite slope. Okay. So the analysis of the finite slope are basically based on the driving moment that cause rotations to the moving soil masses and the resisting moment developed along the failure surface. Keep in mind that the determination of critical failure surface of a finite slope is tedious, okay, by try and error until the safety factor of unity is achieved. Okay, so we may use a try and error, okay, method as well. Okay, for example, using the Bishop, okay, because as I presented the Bishop equation, okay, so they have a two-factor safety on the left and also on the right, okay. So once we assume the factor safety on the right, okay, then we get the factor safety on the left. So we need to make sure that both of the factor safety is equal, okay. So that's why we need to try until 3 attempts, okay. Then we need to use what we call as a methods, okay, whereby we need to plot a graph, okay, until safety factor of unity is achieved, okay. So we may go through the example later on, okay. So with the help of computer program that are available commercially, this task is easily done, okay. Three methods of stability analysis are mentioned here: the total stress analysis for cohesive soil, a method of slices, Arrhenius method, and simplified Bishop methods. So in addition, Taylor charts may be utilized to analyze infinite slope. Okay. Although there is a commercial software, okay, but you need to understand, okay, in terms of how the calculation or the analysis has been carried out. Okay. So because at the end, okay, you can put whatever value inside the software, okay, and definitely the software will provide an answer. Okay, so if you doesn't have a good understanding on the fundamental of the slope stability, okay, therefore, okay, so you need to have a good understanding on the fundamental of the slope analysis, so that you understand or you know what is the relevant parameter to be used in the software. Okay. So we have also here a Taylor chart, okay, as I described in the slide. Okay, we have several different uh, preliminary design chart, okay, but in this lecture we only discuss on the Taylor chart. Okay. Okay, this is the total stress analysis, whereby they use the method of moment, resisting moment over driving moment. Okay, and this is the formula. Okay, so it is better for you to check. Okay, either your book is has been amended or not. Okay, because previously there are some error here on the equation 3.11. So I have do the or on this part, okay, I have do the correction on the soft copy. Okay, so L actually is the length of the arch, okay, r theta. Then r theta times r is a square theta. Okay. Okay, perpendicular. Then we have the theta w x. Okay, so that is for the total stress analysis for cohesive soil. So it could not cater for the unit width of the soil separately, okay, because it is used the total stress analysis. Okay, so that is for the 3.3.1. Okay. Then we have, okay, so this is 3.3.2. So we have here method of slices. Consider a slice having a width B and average height H in figure 3.3. Okay. The developed shear resistance at the base of the slice is due to the width of the slice and internal friction angle based on moment equilibrium. The factor safety, okay, so this is based on the method of slices, okay. So the factor safety is the rising resisting moment over driving moment. Okay. So for this case, okay, we need to construct, okay, uh, as many slices, okay, as we can, okay. The more slices that you have create, okay, I guess the more accurate result that you may have. Okay? So then I will teach you, okay, in terms of on how to draw or analyze based on the method of slices. Okay. Okay, so we have two types of approach, okay, for the method of slices. Okay, the first one is the Fillenius. Okay. Side force on the slice are ignored, assuming the summation of side force is zero. Okay. So this is what assumption made by the Fillenius. Okay. As I told you previously, there is a side force. Okay, the normal and the shearing force. Okay. So the Fillenius has assumed that, okay, side force on the slice are ignored, assuming the summation of side force is zero. Okay. So later on he come up with the equations. Okay. As shown in figure 3.12. Okay. Again, okay, in the earlier in the recent reference book, okay, there is an error there. Okay. I guess the new one, the Kamaru has do the correction. Okay. So please check with your uh, reference book. Okay. So then I, sorry, L, okay, then they have a B, B, W, U, alpha, Phi. Okay. Okay. So when you want to carry out for the method of slices, either using the Fillenius or Bishop, okay, the first thing is, okay, uh, you need to plot in a grid paper. Okay. Why you need to plot in a grid paper? Okay. Because you need to draw on the same scale with the actual conditions. Okay. Okay. The second thing is, uh, for every slice, okay, you need to include the geometry, which is the height and also the width of the slice. Okay. So then, let's say for this case, okay, you find out or you need to determine the center of the each slice. Okay. Okay. In order to solve the problem related to the slope analysis, okay, so you need to bring your protector. Okay. You need to bring your protector. Okay. So the first step, okay, let me show you how to Okay. So let's say this is your slice. Okay. Then the first step is to determine the center position of the slice. Okay. So when you use the grid paper, okay, so easy for you to get the scale. Okay. So for example, if the scale is 4, okay, then you need to draw a 4, okay, to represent the center. You need to put into half. 4 times 2 is equal to 2. Okay. So once you get the center, okay, so extend the center, okay, downward, okay. So the next is to uh, create a line, okay, from what we call the point or the center point. So draw a line, okay, until it extend out from the soil surface. Okay. So use the protector, okay, to determine the angle of the alpha. So hold on it because I have a call. Okay, then use the protector. Okay, so from a protector you will determine what we call as the alpha value. Okay. Okay, as I mentioned previously, okay, so let's say this is the center, okay, of your origin. Okay, then you need to set, okay, um if the alpha location, okay, on the right side, okay, so uh, you may use the positive value, okay, while if the alpha on the left side, okay, so you may use a negative value. Okay, so for this case, the alpha is in a positive value. Okay, so use the protector and then write down the alpha value. Okay, so the rest, okay, you need to put the other parameter, okay, and then try to get uh, the 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 value. Okay, for example, this is the first sub equation. Okay, this is the second sub equation, and this is the third sub equation. Okay, because at the end, okay, to solve the method of slices, okay, so it is better for you to use a table. Okay, put all the information here. Okay, starting from the slice number. Okay, 1. Okay, then normally we use a B. Okay, from there we can get the H. So then we can get the alpha. Okay, until we get all the information. Okay, from there we okay, accumulate the value for each slice, okay, because they are symbol of sum. Okay, so from there we can get the value for the factor safety. That's why, as mentioned previously, it is a tedious work, okay, because it involves several slices and it consumes a lot of time, okay, to complete the analysis. Okay. However, Philenis is more straightforward compared to the Bishop. Okay. Then we look on the Bishop. Force acting on the vertical of the slice are taken into consideration in stability analysis, where the summation of the horizontal force is not zero. Okay, so that is the assumption made by Bishop. Okay, so from there, Bishop come up with the equation. Okay, where they have a m alpha value. Okay, this m alpha value is located on the right, and there is a factor safety. Okay, to be used to factor safety, okay, to be calculated, okay, based on the assumption on the factor safety on the right. Okay. Since Fs appear on the both side of the equation, try and error procedure need to be performed to determine the factor safety. Okay. So that is the step or the procedure, okay, for the Bishop methods. Okay. So then we move to another approach, okay, which is a linear method. The type of the failure occur when a field or an embankment has a weak plane, okay, or when there is an excavation in layered soil and the layer direction is downward to the excavations. Force polygon may be utilized to analyze the slope stability. Both the example of slope and force polygon are shown in figure 3.4. Okay. Okay, so this is the the slope, okay, the infinite slope. Sorry, the finite slope, okay, where the finite slope has what we call as has potential of the uh, failure they call it a failure plane, which is which is the direction is downward to the excavation. Okay. Okay. So in order to use this approach, okay, so we need to refer to this photograph. Okay. So the procedure to determine the stability of this slope, okay, so we may use the try and error approach, okay, where we have a FS phi on the right, and then we also have FSC. Okay, this is FSP, while another one we have a FSC. Okay, so we need to make sure that FSC is equal to FSP. Okay, so the procedure assume a value of SSP. Okay, calculate phi r equal to tangent phi over factor safety phi. Okay, then determine CR using force polygon. Okay, so I will explain, okay, later by using an example. Okay, so then determine FSC. So the FSC is the ratio between C over CR. Okay, then we may get the CR value, okay, based on this equation. Okay, so compare the factor safety obtained in the step 4 with the assumed FS fee in the step 1. Okay. If the FSC is not equal with the FS fee, repeat step 1 to 5 until FS fee is equal to FS fee, or until a curve of FSC again FS fee can be plotted. Okay. So the factor safety, okay, of the slope is equal to FS fee of with the FS fee. Okay. Okay. So that is for the linear failure plane. Okay. Then we move to Taylor chart. Okay. A dimensionless parameter. Okay. We call as a stability number. Okay. Obtained by the correlating the slope, by correlating the unit width and cohesion of the soil, and the height of the slope is plotted as a function of the slope angle beta for various value of internal friction angle of the soil. Okay. For a slope of soil with phi 0 and beta less than 53, okay, the failure surface is deep below the crest of the slope and must be correlated to the depth of the slope to the underlying hard stratum. Okay. For the C phi soil, trial and error procedure as follow need to be undertaken to analyze the slope stability. Okay. So we need to refer to the chart, okay, for the Taylor. So actually the chart is at the appendix. Okay. So you may refer to the appendix to for the Taylor. Okay. So again, we may discuss later on, okay, based on the example. Okay. The same approach with the linear failure plane, okay, where we use the try and error methods. So we have here as a FSV, okay, then later on we need to make sure that the FSC is equal to the FSV, okay, then repeat until we get the same value of the FSV and also the FSC. Okay. So that is for the introduction part on Dr. Kamarudin. Okay. Okay. So now we move to the problems and solutions. Okay. So figure Q3.1 illustrate an infinite slope of C and phi soil. Okay. Assuming the groundwater table is far below the slope surface, calculate the developed shear strength S and shear stress tau along the failure surface. So in this case, we need to refer to equation 3.1 to 3.4, okay, because it doesn't have any seepage. Okay. So then the value of the alpha, sorry, the value of gamma, C and phi, okay. Then we have here the I, which is the gradient of the slope, 10. Then the height of the slope is equal to 5. Okay. Okay. So the developed shear strength can be determined using equation 3.1 and 3.2, 3.3 and 3.1, okay, where S is equal to C plus sigma tangent phi, okay. So then the sigma is equal to gamma H cos square I tangent phi, okay. So 20 is the C unit weight, 18 times 5 is the height. Okay, cos square 10 I is tangent is the 10. Okay, and then we have tangent 15, which is represent the phi. So the value for the S is equal to 43.4. Okay. So the next is the shear stress. Okay. So the shear stress is gamma times H sin I cos I. Okay. Gamma is 18 times 5 times sin I times cos I. Okay. So then we get the 15.5, 15.4. Okay. So actually, to get the value for the factor safety, S should be divided with tau. Okay. So the value is about, 43.4 divided with 15.4. So it is 2.81. Okay. So it's greater than 1.5. Okay. So we can consider the slope is in a good in a stable condition. Okay. So that is for the slope for the infinite condition. Okay. Okay, if you have any questions, so you can ask. Okay. So then we have example number 2. Okay. So consider an infinite slope of C and phi. Okay. So as shown in figure Q32. Okay. So this is the slope. Okay. Determine the safety factor against sliding, okay, assuming the interface friction angle between the sliding and the statutory subsoil is 20. Okay. So that is number A. That is for A. Okay. B, determine the critical height of the slope. Okay. Means that what is the height, okay, if the value of the factor safety is equal to 1. Okay. So the C, okay, determine the safety factor against sliding. Okay. If the groundwater table is at 2 meter, okay, below the slope surface and seepage occurs. Okay. Use the saturated unit weight of soil 19 and assume other parameter are unchanged. Okay. So the first one, similar with the first example. The A, okay, similar with the first example. Okay. Then the B is try to get the height. Okay. When the factor safety is equal to 1. Okay. The C, by using the same figure. Okay. But assume that the water is 2 meter below the slope surface. Okay. What is the safety factor value? Okay. The developed shear strength and shear strength along the failure plane must be considered to determine the safety factor of the slope. Okay. Therefore, S over tau. So we use the same equation with the first one because it doesn't have any seepage and it is a cohesive type of soil. Okay. So the value is equal to 1.5, okay, for the factor safety. Okay. Then we look on the B. Okay. Critical height of cohesive soil can be determined by taking the factor safety equal to unity, which is factor safety equal to 1. Those equating equation 3.3 to equation 3.2, okay, will become like this. Okay. Then rearranging, okay, then we obtain, put the H on the left while the rest on the right. Okay. So then we try to solve by put all the important parameter or related parameter in the equation. Then the height of the slope under the critical condition is equal to 21. Okay. That is for B. Okay. So then C, note that this problem involves the combination of soil above and below the water table. Hence, the appropriate unit weight of soil and strength parameter must be selected and applied judiciously. In order to enhance the understanding, the proper step will be illustrated. Okay, illustrated. So we have the S and also the tau. Okay. As I mentioned previously, okay, the tau, okay, the unit weight or whatever soil properties, okay, especially unit weight. Unit weight doesn't the what we call the soil, the water doesn't shear, so we should not eliminate the value for the unit weight of the water in the calculation. Okay. So then we have here S is equal to C plus normal stress tangent phi. Okay. So this is the value for the unit weight times H, which is 70. So then the S is equal to 50.93. Okay. So for the tau, okay, this is the formula. And it is stated here, since water cannot resist shear stress, so no need to eliminate the unit weight of water, okay, to get the effective unit weight. Okay. Reader may refer to other reference for the derivation. Yes, when I refer to another reference book, so they also use the same approach. Okay. Then we do the calculation to get the tau. So we obtain 42.13. Okay. So the ratio between 50.93 over 42.13, so we obtain 1.21. Okay. So when the water is increased, okay, so the factor safety has been reduced. Okay. The first factor safety, okay, when the water is far, is 1.5. Okay. And then when water is increased, okay, up to 2 meter below the surface. So the the factor safety has been reduced to 1.21. Okay. So that is for the example number 2. Okay. So like if you understand the example number 2, okay, I guess you have mastered on the infinite slope problems. Okay. So because normally the question will ask, okay, what is the critical height? Okay. So what is the factor safety? Okay, when the water is increased. Okay. Yeah. Or they provide the factor safety value. Then you need to determine what is the C, for example, or phi value. Okay. After they have provided the factor safety value. Okay. Okay, that's for number 2. Okay, now we move to number 3. Okay, this is the Philenis example. So we need to count the 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 factor safety value for the slash number 3 and also slash number 6. Okay. Okay, but in order to get the factor safety value for the whole, So we need to solve from number 1 slash number 1 to slash number 7. Okay. So we look first on the example. Okay. So the first procedure, as I told you before, so it is better, okay, to plot the problems on the grid paper, okay, because it is easy for you, okay, to what we call to calculate, okay, or to determine the height for each slice and also the width of for the each slice. Okay, so we try to solve the problem number 3 and the problem number 6. Okay, so this is the parameter for the soil number 1 and soil number 2. Okay, so this is the soil number 1 and this is soil number 2. Okay. So as I told you previously, okay, the alpha is very important. Okay, so beside that, okay, you need to look on the failure plane. Okay. So for the failure plane, you need to make sure that the failure plane only cover for one type of soil only. Okay. Okay. So when you want to draw for the slice, okay, you need to make sure that if you have a two different layer of soil, okay, you need to make sure that your failure plane, I call it as a FP, okay, failure plane should be located on one type of soil. Okay, let's say, okay, number 6, okay, and number 7. Okay, so when you draw the what we call the slice, okay, okay, you cannot combine the number 6 and number 7 as a one slice. Okay, let's say if you combine, okay, as a slice number 6, okay, so later on you may find out that the failure plane, okay, for the slice number 6 is different type of soil compared to the slice number 7. Okay, so we need to make sure that only one type of soil, okay, on the failure plane, okay, because if we have two type of soil, so it is very difficult for us, okay, to differentiate or to analyze, okay, by including two type of soil on the resisting moment. Okay. So that's why we need to differentiate. Okay. However, for the slice body, so it doesn't problem. It doesn't have any problem. Okay, although it cover two type of material. Okay, let's say for the size number 6, we have soil number 1 on the top and a little bit of soil number 2 at the bottom. Okay. But for the slash number 7, it only cover or it only consists of slash number soil number 1 only. Okay. So that is the rule, okay, for the method of slices. Okay. Okay. So we move to the slide number 3. Okay, we have two soil parameter. Okay. The weight of the slide is calculated based on the gamma VH. Okay. So this is you need to look on the full equation. Okay, so the full equation. Okay, this is the full equation. Okay, the full equation. So we have three sub equation. Okay, the first one is the CL. Okay, the second one is the W cos alpha minus UL tangent phi, and the last one is the W sin alpha. Okay. So the first thing you need to determine what is the W. Okay. Then from there you can start to choose, okay, which equation that you want to solve, either number 3, number 2, or number 1. Okay. Because we have a 3 sub-equation. We cannot, it's not suggested to solve the whole equation with a 1 calculation. Okay. So we need to solve one by one. Okay. Okay, first we determine the W. Okay, from the W, what should we do? Okay, so this is the slice number 3. Okay, first get the width of the slice. Okay, so we need to count how many box. Okay, because 10 box, 5 box is equal to 10. Okay, so it means that each box the scale is equal to 2. Okay, so we have 10 because 5 times 2, 10. Okay, so 10 divided with 2, it will become 5. Okay, then we need to draw a line. Okay, so to determine what is the height of the slice. So this is H, but this is B. Okay. So that is for the slice number, and that is to determine the weight. Okay, so 18 is the unit weight, B is the width, H is the height. Okay, for the soil number 1. Okay, so 19.5 is the soil number 2 unit weight, B is the 10, okay, and 12 is the height of the soil number 2. Okay, so this is soil number 2, while this is soil number 1. Okay, so then we obtain 80. Okay, so that is for the W. Okay, so then we try to solve the sub-equation number 3. Okay, while this is sub-equation number 1. Sorry, 1. This is 1. While this is sub-equation number 2. Okay, so the sub-equation number 3, we have their sign alpha. Okay, so the value is negative. Okay, as I told you before. Okay, okay. Sorry. Okay, so if the alpha is located on the left, okay, so we may consider as a negative. Okay, so we may consider as a negative. Okay, okay. Meanwhile, okay, if the alpha is on the right from the origin, so we may consider as a positive. Okay, so for the slice number 3, the alpha is on the left, so the author has considered as a negative. Okay, so by using the protector, okay, the value of the alpha is equal to 10. Okay, so then negative 656.39 is the value of the W sine alpha. Okay, so then we have a CL. Okay, C is the cohesions. Okay, B is the width over cos alpha. Okay, so cos alpha is negative 10. So the value of the CL is 355.4. Okay, for the B case, okay, the C is referred to the soil number 2, okay, because the C used for the resisting moment. Okay, so the value for the soil number 2 is equal to 30. Okay. Sorry, 30. Okay, sorry, C. 35, not 30, 35. That is for the fee, okay? So not use 30 because it is soil number 2, not soil number 1. Okay. So the value is 355.4. Okay. Then for the W cos alpha tangent fee, okay, the value is 2,149.23. Okay. So that is for the slide number 3. Okay. So now we move to the slide. Okay. That is for the slide number. Okay, slide number 3. Okay. So actually this is slide number 6, not slide number. Okay. So then we put all the information here. Okay. To get the value for the sub equation number 1, sub equation number 2, and sub equation number 3. Okay. Then we have the slide number 6. Okay. For the slide number 6, we calculate for the W. In the same procedure. W sin alpha. Okay. This case, alpha is equal to positive because it is on the right side. Okay. Then the same procedure. Okay. As similar to such numbers 3. To get the CL, okay, and that to get the W cos alpha tangent phi. Okay. So taking note, the strength parameters C and phi used in the calculation are those at the base of the respective slice. The negative angle value indicate the position of the slice is resisting sliding. Similar processes are to be undertaken on other slices to obtain the overall safety of the slope with the trial failure surface. Okay. So that is for the example number 3. Okay. So when we look on this example, okay. So we need to solve, if you want to get the value for the factor safety, so we need to solve for each slice, okay. Then need to add, okay, a driving moment, okay, from the road, okay. You can see there is a road, okay, on the slope, okay. So you need to consider this as a part of the driving moment, okay, because it has a weight. Then we need to multiply the weight with the moment arm, okay. So it is a part of the driving moment. So should be put on the sub-equation number 3. Okay. Where's sub-equation number 3? Okay, then need to add for this additional. Okay, so need to add the road. Okay. Okay, so that is for the slide number. Sorry, that is for the example number 3. Okay. Okay. So next week is your last class, correct? Hello? Hello?
Yes, doctor.
So I will continue next week, okay, for another 1 hour. Okay. Then we will have a break. Then later on we may continue for test 2. Boleh?
Okay, doctor.
Okay. Then we may continue for the test 2. Okay. The test 2 only cover for chapter 2 under the consolidation. So I will use the Google form. Okay. So then you need to upload your calculation, okay, during the submission. Okay. Any question? Hello? Okay.
How many questions for
How many
the
questions?
test?
So the test, okay. Yeah, I will allocate 1 hour for your test. Okay. How many questions? The test has been designed for 1 hour.
Okay, noted.
Okay. Okay. So see you next week. Then I will upload this recorded class in the e-learning. Okay. Okay, about the attendance, I will share the attendance right after the class, the QR code. Okay, see you for next week. By the way, okay, on the remaining example, okay, so can somebody help me to scan? Okay, okay, this is example number 4. Okay, I'm not sure for the new books. Okay, so how many example for the chapter 3? Okay, this is number 5. This is number 6. This is number 7. This is number 8. Okay. Number 8. Okay, only number 8. How many example in chapter 3 for the new book?
9.
9. Okay. Afika boleh tolong?
Boleh.
Nanti Afika share dengan saya satu yang example number 9 ni.
Okay. Doktor, boleh tak doktor share note yang lecture chapter 3?
Okay, yang lepas boleh. Boleh? Saya upload
Okay, thank you doktor.
Okay. Okay. Terima kasih. Assalamualaikum and good afternoon.
Thank you doktor.
Thank you, Doctor.